Hello again everyone, this is Vincent and this is episode 6 of the Steambirds Survival Let's Play on Kongregate. If you watched my last video, which was the Steel Sentinel City mode video, you'll know that my commentaries for the next couple of videos are going to be me talking about my different subjects, while at the same time trying to entertain by doing it in a different accent. Which is probably not going to work anyway. In this video I'm going to be talking about chemistry, and I'll try to do it in a British accent. So today's commentary is on the atomic structure in terms of chemistry. This is sort of the boundary between physics and chemistry, but I'll be taking it from the chemistry perspective. This is sort of background knowledge, maybe. Almost common knowledge. Not really. But you learn it in grade 8 or 9. Basically, the atom is made up of three subatomic particles. The proton, the neutron, and the electron. Although this is technically a theory, this is the best theory out there that exists at the moment, and no one's been able to falsify it for the time being. In the atom, you have the nucleus, which is made up of the positively charged protons, and the neutrons, which have no charge, which contribute 99% of the mass of the atom, and then you have the electrons orbiting the nucleus, which don't have a lot of mass at all. The proton and the neutron weigh approximately the same, and the electron weighs approximately, I think, 2,000 times less than the proton. So, in chemistry, we have a concept known as the atomic number, and the atomic number is basically the number of protons in the nucleus, and the atomic number is what makes each element unique. So hydrogen will always have one proton. Helium will always have 2. Uranium will always have 92, and so on and so forth. However, because there are neutrons in the nucleus, which also have mass, there is also a quantity known as the mass number, obviously, which is defined by summing the number of neutrons and the number of protons. We ignore the electrons because they have a fairly negligible mass. And changing the mass number of a nucleus does not change the element unless you change the number of protons, but it does change a few of the properties. You can work out how many neutrons, protons, and electrons are in a particular atom by looking at the mass number, the atomic number, and the charge. The atomic number is pretty much just the number of protons, as I said before. The mass number, which is equal to the number of protons plus the number of protons plus neutrons, and the number of electrons can be worked out from the charge, because protons have a +1 charge, so you multiply +1 multiplied by the number of protons, and given a charge, and if you add the number of electrons in a particular atom, you'll get the final number is a charge. So in a neutral atom which has no charge, the number of protons is equal to the number of electrons. Now here it gets a bit more complicated, because, as I said before, changing the number of neutrons in a nucleus does not affect what element it is, but it does change the mass. So you can expect that in most elements, you can have a slightly different number of neutrons in each nucleus. So, for example, chlorine has two forms: chlorine 35 and chlorine 37. But both chlorines, because it's chlorine, has 17 protons, but the number of neutrons is slightly different. One has 18 and one has 20 neutrons respectively. And because of that, it has the nuclei have a slightly different mass. Now, these different forms are known as isotopes. And these isotopes in a naturally occurring sample, or pretty much just like harvesting it from any old place, will occur in a certain proportion known as the natural abundance. So coming back to chlorine 35 is approximately 75% of naturally occurring chlorine, while chlorine 37 is about 25%. And so if you would have, say, 100 atoms of chlorine, you'd expect that 75 of them were chlorine 35 and 25 of them were chlorine 37. And knowing the different masses and their proportions, you can figure out the mass of that particular sample. So if you were to have 100 atoms, 25 of them would have an atomic mass of 35, while 37, while 75 of them have an atomic mass of 35. If you divide by 100, you get the average mass of each nucleus. And because all samples, naturally occurring samples, have this natural abundance or proportion of these isotopes, you can figure out an average mass of each nuclei. And the average mass of each nuclei is 35.5 atomic mass units. And using some other maths and chemistry, we define that chlorine has a molar mass of that a chlorine atom has a molar mass of 35.453 grams per mole, if you know what moles are. We can also backwards engineer this process. If you know the atomic mass of a nucleus, you can figure out the natural proportions, given that there are only two different forms it can take. Just using some algebra, let X be the proportion of a particular isotope, and the other isotope must take the proportion of 100 1 minus X. Then multiply each isotope mass by its proportion. Then you get the molar mass, and you just solve for X. So because different elements can take different isotopes with different masses, generally the average nuclear mass of a nucleus is not an integer. Although if they are sort of 50-50, you can get an integer even if it's neither of those integers. If neither of the nuclear masses are that integer. And we can apply the fact that different isotopes have different masses because some isotopes are actually radioactive, but because they are the same element, they act chemically and therefore biologically as the same element. So radioactive iodine and normal iodine will be absorbed by the thyroid in the same way, and you can use it. But because one isotope is radioactive, you can use it to trace the iodine in the thyroid. I think that concludes this commentary for now, and I'll see you in the next episode. This is probably a bad British accent, and I'm sorry if I offended anyone, but I'll just see you in the next video.